Today I am going to discuss on how we can determine an empirical formula and a molecular formula for a compound when we are given the masses or the percent compositions of the elements or the atoms in its compound. Okay, so before that, uh, we need to know how we can determine the percent composition of the compound. The percent composition, what is that? The percentage of a mass of a percentage of an element will be given by its mass. So in order to find this percentage by mass of an element, we need to divide the atomic mass of the element multiplied by the number of atoms in its element in the molecular formula, and we divide that by the molecular or formula mass of the compound, and then we multiplied it by 100. Okay, as an example, let's calculate the mass percentage for hydrogen and oxygen in this hydrogen peroxide. When you look at the molecular formula of hydrogen peroxide, how many hydrogens are in 1 mole or molecular formula of hydrogen peroxide? Yes, the number of atoms per each element will be given by this subscripted number. So there are 2 hydrogens per 1 mole of hydrogen peroxide. How many oxygens in this molecular formula? Yes, so we look at this subscripted number. So it is 2. So how many oxygens? Yes, there are 2 oxygens in 1 mole of hydrogen peroxide. So let's calculate the percentage of hydrogen. So the N is the number of atoms per 1 molecular formula. It is 2 for hydrogen. Then I multiplied it by the atomic mass of hydrogen. So where should I get this atomic mass of elements? Yes, you look at the periodic table and you will get these atomic masses of those elements from the periodic table. So the atomic mass of hydrogen is 1.008, and then we divide it by the molecular formula mass of compound. So how we can find the molecular or formula mass of this hydrogen peroxide? Yes, we get the masses of the atomic masses of hydrogens, and we multiplied it by 2, and we add it to the or the mass of oxygen multiplied by 2. Okay, so we add these two together, then we get the molecular mass of or formula mass of the hydrogen peroxide. So we found it as 34.02 for this hydrogen peroxide, H2O2. Then we multiplied it by 100 and we get the percentage as 5.926. That is the percentage mass of the hydrogen in the H2O2 in hydrogen peroxide. Let's calculate the percentage mass of the oxygen in hydrogen peroxide. The N for oxygen in hydrogen peroxide is 2 again, and we then multiply that by the atomic mass of the oxygen, that is 16. So then, okay, then we divide it by the molecular mass of the H2O2, that is 34.02, and we multiplied that by 100. So we get 94.06. Okay, so we calculate the mass percentage of hydrogen and mass percentage of oxygen in hydrogen peroxide. Okay, so if this hydrogen peroxide, okay, the hydrogen peroxide has only hydrogen and oxygen. So if I add these two percentages, what should I get? Yes, I should get 100% because in this compound, in this hydrogen peroxide, I have only hydrogen and oxygen. Let's see how we can do this sample problem. It's asked us to find the percent composition of by mass of lithium carbonate. So we need to give the composition in this compound by its percent by its percentages. So we will give it by percentage of masses for lithium and how many are there any two different elements or three different elements? There are three: lithium, carbon and oxygen. So you need to give all three percentages for these three different types of elements in this lithium carbonate. The first thing, we need to calculate the formula mass of lithium carbonate. So we take the periodic table and we find the atomic masses of lithium, carbon and oxygen. Right. So how many, the atomic mass of lithium was found as 6.941, and how many lithiums are in this lithium carbonate? Yes, there are two, and I multiply this 6.941 by 2 and add, then I get the atomic mass of carbon. It is 12.01. Then I am going to add the atomic masses come from these oxygens. There are three oxygens in this molecular formula. So I multiplied the atomic mass of oxygen by 3. So altogether, the sum of this calculation, I get it as 73.89. So that is the formula mass or the molecular mass of lithium carbonate. Now, I'm going to give the percentages for lithium, for carbon, and for oxygen. So in the numerator, I should get the component from the lithium. There are two lithiums multiplied by the percentage atomic mass of lithium divided by the formula mass of the lithium carbonate multiplied by the 100. I get 18.79% for the lithium. Then I calculate the percentage mass of carbon. There are only one carbon in the formula. So it is just multiplying by 1. So you can mention it or you do not have to mention it if you are multiplying something by 1. So then I mention the atomic mass of carbon. It is 12.01 and divide by the formula mass of this lithium carbonate, that is 73.89, and multiplied by 100. I get 16.25% for carbon in this lithium carbonate. Then the oxygen. So there are three oxygens. So I multiplied by starting the calculation by multiplying 3 and by the atomic mass of oxygen, that is 16.00, and divide it by the formula mass 73.89 and multiplied it by 100. You get 64.96 as the answer. So we give the we gave the percent composition of the mass of lithium in this lithium carbonate. So the lithium has 18.79 percentage by mass and carbon has 16.25 percentage by mass and oxygen has 64.96 percentage by mass. So if I add all these three percentages, I will get 100%. Okay, I hope now you will be able to calculate the percent compositions of a given compound. So how you going to calculate the percent compositions? Yes, you will you get the atomic masses and you multiply these atomic masses by the number of atoms in the formula and you divide that by the mass of formula or the molecular mass and you multiply that by 100. Okay, now we are going to we are going to determine the empirical formula by percent compositions. What? So before we are going to calculate or we are going to determine the empirical formula, we should know what is a empirical formula. Empirical formula will give the simplest ratio of between the elements, between the atoms in a molecular formula. Okay, what is that? Let's do an example. I would say H2O2. That is the molecular formula. What is the empirical formula? I will give the simplest ratio between the atoms. Then I will divide the everything by its smallest number. So then what would be the empirical formula for the H2O2? It would be HO. That is the empirical formula for the hydrogen peroxide. Okay. You want to do another example? Okay. Let's look at the sulfuric acid, H2SO4. So what is the empirical formula for this H2SO4? Yes, that is the simplest ratio, right? So that is the lowest, the smallest ratios we can given. The empirical formula should be the simplest ratio given by the integers, given by the positive integers. So we cannot give the decimals or the fractions. So therefore this H2SO4 is the molecular formula as well as the empirical formula. So I hope now you understand the difference between an empirical formula and a molecular formula. Oh, let's move on to the next sample problem. Now we are asked to determine the empirical formula of a compound that is 30.45% nitrogen and 69.55% oxygen by mass. So what are the two elements that this compound have? Yes, it is nitrogen and oxygen. What is the percentage of nitrogen? Yes, it is given as 30.45%. And what is the oxygen percentage? It is given as 69.55%. Okay, so let's see how we can determine the empirical formula. So when we are given the percentages, then we assume there is a 100 gram of sample. Remember, when you calculate, when you add all these percentages, you always get the number, the total as the 100. So we assume there is 100 grams of sample and we have 30.45 grams of nitrogen and we have 69.55 grams of oxygen in the sample. That is the first assumption that we'll make. Okay. So now the computer formula, we'll write it as N subscripted X and O subscripted Y because this compound has only nitrogen and oxygen. And we assume that the percentages, that now we have 100 grams of sample where we have oxygen as 69.55 grams and we have nitrogen as 30.45 grams. And now we need to change these grams of these substances or the elements to their moles. So how we can change the grams to moles? What do we need? Yes, we need the molar mass of those compounds. Where do we get those molar masses? Yes, from the periodic table. So the molar mass of nitrogen is 14.01 and molar mass of oxygen is 16.00 grams per mole. Right. So now I'm going to find the moles of each element in this molecular formula. So there is only 30.45 grams of nitrogen. So I change it into the moles of nitrogen. So I divide that by 4 because 1 mole of nitrogen weighs 14.01 grams. So grams of nitrogen to grams of nitrogen cancel out and I get 2.173 moles of nitrogen. Then I am going to calculate the moles of oxygen in this compound. So I start with the mass of oxygen. So we assume there is the percentage is equal to the grams. So 69.55 grams of oxygen multiplied by 1 moles of oxygen divided by the 16.00 grams of oxygen. Grams of oxygen to grams of oxygen cancel out and I get 4.347 moles of oxygen. Okay, now I got the proportions of moles for the nitrogen and oxygen in this complex. If I write it like that, N subscripted the moles of nitrogen, it is 2.173 and then I write the oxygen and then I write the subscripted number as its moles, 4.347. Is that the empirical formula? Now I should give the simplest ratio in positive integers. So how can I make this decimal value to an integer? Yes, I am going to divide the each and everything by the smallest number. You divide it by the divide the every number by the smallest value. So the smallest value is 2.173. So I divide by, if I divide the n by 2, okay, 2.173 by 2.173 will be equals to 1. And then I divide the 4.347 by 2.173. I'll get it around 2. When you get something like 1.98, 1.8 or something, then you should round it to the nearest integer. You need to present this empirical formula in positive integers. So I got these integers as 1 and 2. So I'll write the empirical formula as NO2. Is it clear for you all now? Okay. We are going to determine the empirical formula and a molecular formula for a compound. The combustion analysis is a method, it is an experimental method that will find the percentage of the or the masses of the compound. It will help us to calculate the or determine the percentage masses or percent composition of a compound. In a combustion analysis, what would happen is we will burn an hydrocarbon. Okay, how we can burn a hydrocarbon? Yes, we need to supply oxygen. And then we collect, then when a hydrocarbon is burned with oxygen, it will change to, it will give H2O and CO2. All hydrocarbons will change to, will give water and carbon dioxide as product. All hydrocarbons have carbon and hydrogen. But sometimes some hydrocarbons may have an oxygen, okay? Or some compounds have sulfur and nitrogen, or like those things, right? Okay, here you will see a picture of the combustion analysis. Here the sample is burned and here it provided the oxygen, and first it will go through a copper oxide. It will get the or absorb the residues or something unburned things, and then this air will be moved. The carbon and hydrogens will be turned into gases, the water, the vapor, and the carbon dioxide, and then it will be gone through a H2O absorber. In this chamber, all the H2O vapor will be absorbed to this layer. Next, it will be forwarded or directed to a carbon dioxide absorber, and this absorber will get all the carbon dioxide. Then the differences of these masses will give the mass of water and the mass of carbon dioxide. We get the initial masses of the absorbers, then we set the experiment on. After the experiment is completed, we'll get the final masses of these absorbers. The differences of these masses will help us or will let us calculate the masses of the H2O and the mass of the carbon dioxide. I just explained the method of this combustion analysis, or what's going on during a combustion analysis. All right. Okay, here is an example how the empirical formula of this organic compound. It is glucose. You all have heard and used these. So the empirical formula of the glucose was found by the combustion analysis. Let's read the question. When a compound such as glucose is burned in a combustion analysis apparatus, it will turn the carbon dioxide and water are produced. Okay, so then, then you will see the glucose. What are the elements that in glucose? There are carbon, hydrogen, and oxygen. But why we cannot find a method to find the oxygen in this compound? We can't do that because we are giving the oxygen in to get the burning. So if we are not calculating the percentage of the mass of the combustion analysis is not, it does not give us the mass of the oxygen even in an indirect method. But if we know the masses of the carbon and if we know the mass of the hydrogen, can we find the mass of oxygen? Yes, that's right. Because if we know the mass of the sample and if we know the mass of the carbon, if we know the mass of the hydrogen, the rest will be for the mass of the oxygen. Good. Okay, let's see how this experiment has been done, and let's look at the results we obtained from this experiment. Suppose that in one such experiment, like in a combustion analysis of glucose, the combustion of the 18.8 grams. That is the mass of the sample we inserted into the device. The glucose produced 27.6 grams of carbon dioxide and 11.3 grams of water. Right. But do we need the grams or moles of carbon dioxide or the water? No. We are going to calculate the masses of the carbon from the carbon dioxide and we get the mass of the hydrogen from the water. How we can do it? Yes, we'll start with the mass of carbon. It is, we are going to determine the mass of carbon. We start with the mass of the carbon dioxide. It is 27.6 grams of carbon dioxide. And when you look at the carbon dioxide, in 1 mole of carbon dioxide, how many moles of carbons? Yes, 1 carbon. If you look at the 1 mole of water, how many moles of hydrogens are there? Yes, there are 2 moles of hydrogens. We need that relationship to calculate the masses of carbons and hydrogens. So we starts with the mass of the carbon dioxide. Now we'll change it to moles of carbon dioxide. So we divide that by the molar mass of the carbon dioxide. Then more grams of carbon dioxide to grams of carbon dioxide cancel out. And now we have the answer in moles of carbon dioxide. Now we can have a relationship between the carbon dioxide and the carbon. Yes, in 1 mole of carbon dioxide, we have 1 mole of carbon. Then moles of carbon dioxide to moles of carbon dioxide are cancelled out and we get the answer in moles of carbon. Do you know how to change the moles of carbon to the grams of carbon? Yes, you need the molar mass of carbon. Alright, so 1 mole of carbon weighs 12.01 grams. So after you solving this um, calculation, you get 7.53 grams of carbon in this 18.8 grams of glucose sample. Okay, let's calculate the mass of hydrogen. We start it from the mass of water. It is the 11.3 grams of water. Now we change the grams of water to the moles of water. We use the molar mass of water. So more grams of water, 2 grams of water is cancelled out, and then we get the moles of water. In 1 mole of water, there are 2 moles of hydrogens. So moles of water to moles of water cancel out. Now we have the answer in 2 moles of hydrogen. Moles of hydrogen, and you change the moles of hydrogens to the grams of hydrogen by using the molar mass of hydrogen, and you get the final answer as 1.26 grams of hydrogen. So in this sample of glucose, the 18.8 grams of glucose, we have 7.53 grams of carbon and 1.26 gram of hydrogen. Okay, so how we can find the mass of oxygen? Yes, the remaining mass will be the mass of oxygen. We subtract the mass of carbon plus the mass of hydrogen, 7.53 plus 1.26 from 18.8 grams. That is the sample with what they have started the experiment. And the remaining mass, the difference will be the mass of the oxygen. Now we have the mass of carbon, we have the mass of hydrogen, now we have the mass of oxygen. Get? Yes. Now you can think of a way to calculate the empirical formula. You have the masses. So then what you are going to calculate? We have the masses. Then we get the percentage of the masses. Good. Then you can follow that method to calculate the empirical formula. So we calculate the moles of carbon. 7.53 grams of carbon divided by its molar mass of carbon. I get 0.627 moles of carbon. Then I am going to calculate the moles of hydrogen. The mass is 1.26 grams for hydrogen, and you divide that by its molar mass. It is 1.25, and we found there is only 10.0 grams of oxygen in that sample of glucose. So we divide it by the 16.00 and we get the answer 0.626 moles of oxygen. So if I write it in this formula, carbon subscripted 0.627, hydrogen 1.25, oxygen 0.62. Is that all? Are we finished? No, we cannot give the empirical formula in decimal values. We should provide it with the positive integers. So how can I change these decimals to its positive integers? Yes, I divide the every value by the smallest number. So what is the smallest number? Yes, 0.626. So I divide this by 0.626. I get 1. If I divide this by 0.626, I'll get around 1. And when I divide 1.25 by 0.626, I'll get the answer is round to 2. So now do I have positive integers? Yes. So this calculation shows you how the positive integers were obtained. And then the formula, what would be the formula? Carbon, hydrogen, 2, and oxygen. You don't have to write the 1. Okay, but even though you don't write 1, we all know if there is nothing in there means it is 1 in this molecular form, any chemical formula. Okay, so this is the empirical formula for glucose. Okay, now we are going to determine the molecular formula for the glucose. What is the empirical formula? Yes, this is the empirical formula. We are given a fact. We are given a fact. It says the molar mass of glucose is 180 grams. Where we should start with then? Yes, we have the more empirical formula. So what we should do now, we'll calculate the more formula mass of this empirical, we calculate the mass of this empirical formula of glucose. So it is 30. How did you get the 30? The molar mass of carbon is 12.01 and there are 2 hydrogens, 2 multiplied by 1.008 plus the molar mass of oxygen, it is 16. So I get 30. Right. So the molar mass of glucose is 180, but the empirical formula mass is 30. That means the empirical formula is not the molecular formula of the glucose. So how can I get the correct molecular formula? Yes, I divide the molar mass by its empirical formula mass. 180 divided by 30. Okay, I get the ratio as 6. So what does that mean? There are, like it tells, like there are 6 empirical formula units per 1 molecule of glucose. So if I need to get the molecular formula, so this is the empirical formula, I should multiply it by 6. What does that mean? So what is my molecular formula then? It would be C6, H, 2 by 6 is 12 and O6. That is the molecular formula of glucose. So this is the molecular formula of glucose. This in your PowerPoint slides, there is another example was given, and the the setup and the solution was also given. So please practice these questions. Okay, so then that would be very useful for when you are studying for your quiz from this chapter 6.